This is On the Future of Flight Software. I am Kristen Yvonne Rosier, and I'm excited to talk to you today at Splash 2020 about this topic. I wanted to start with a recent news article. So we have, of course, all heard all of the news stories that were splashed all over about the Boeing 737 MAX and the software error that famously took down the Ethiopian Airlines and Lion Air flights. But this is not limited to one or two bugs that make headlines every now and then. Software, especially in flight, is a really hard problem. And even the 737 MAX that has been continuously undergoing review and very intense scrutiny of its software, revising that so that it can become recertified and that Boeing can fly it again. Even in April, this is April 2020, so this year, when we had already entered the COVID pandemic and largely stopped flying, we were still getting news articles with new errors, for example, to the 737 MAX software. This one reported that Boeing had been making 2 new upgrades to the MAX's flight control computer as the company seeks to return the 737 MAX to the skies. Boeing said one of these issues involves hypothetical faults in the flight control computer microprocessor, which could potentially lead to a runaway stabilizer, while the other issue could potentially lead to disengagement of the autopilot feature during final approach. The new upgrades will fix both issues, and the FAA says it remains in contact with Boeing as this company continues its work on the automated flight control system of the 737 MAX. So you can see these are not small issues, and they keep coming up as we do additional code review and try to fix flight control software. This is not an isolated incident. This is less than 2 weeks from that article. Here is another one, an article dealing with a different plane. These are all from the AIAA Daily Launch. AIAA is the American Institute of Aeronautics and Astronautics. It's the professional society for aerospace engineering. And in this one, the FAA was ordering Boeing to fix computer issues on the 787 cockpits that could lead to incorrect flight data being displayed. Specifically, the order responds to a report that the 787's Common Core system, an all-software system, can experience data monitoring problems after the system has been continuously powered for 51 days, which is not weird for an aircraft, especially one making commercial flights. Data monitoring problems can cause issues with the 787's Common Data Network, which handles all of the flight critical data, including airspeed, altitude, attitude, and engine operations, says the FAA's order. Consequences can include display in the cockpit of misleading attitude, altitude, airspeed, and engine operation data, says the FAA, or the engine could lose stall and overspeed warnings. So this order requires all of the airlines to complete actions to fix this issue. You can see these are not small issues. This is why flight software is so critical. These are the core operations of the aircraft. And this is just yet another article that comes out in the daily news. And this isn't, nothing crashed here, right? This is something that was found without anyone being harmed, thank goodness, just in software testing. But these kinds of things happen all the time. Unless you think I'm picking on one company, I'm not. This happens to everyone who deals with flight software. So here is a similar article. I cut off the article because it's basically the same content, but this is dealing with Airbus. And in this case, Airbus had been chasing a software glitch in a troop carrier that it had produced, and the money spent on chasing down this software glitch hit $7.35 billion, which is what triggered this headline. So we're not just talking about critical functionality and of course human life that we can't put a price on. We're also talking about lots of real dollars just trying to track down a software glitch that prevents a plane from being able to fly. This happens, like I said, to many companies. Here's another article from Saab on a different aircraft, their Gripen E. They call it the flying computer, and there's a reason why it got delayed. The reason is flight software. So again, exactly the same problems. Software glitch, it's hard to find. This is critical when we're talking about an aircraft craft. No one died, but we still can't fly this aircraft. Unless you think that it's just safety, we also have security. So here is a headline that was also generated in the recent past where a Boeing 757 was hacked. And the Department of Homeland Security is worried about the risk of planes. So cybersecurity is a unique problem in aerospace engineering because it has all of the regular problems that make it hard from just the normal software engineering community, but also the fact that when you're talking about flight software, oftentimes you're talking about systems that by definition only work if everyone knows how they work. And so you can't obscure things or encrypt things or otherwise have the same level of restriction of access that you could to help solve this problem in other software domains that aren't dealing with flight. And one of my favorite little anecdotes was one time when I was a civil servant at NASA, I was working on software for an air traffic control protocol. And the PhD student who I was advising on the project happened to have Chinese citizenship. He was a PhD student in the US, but like many, many PhD students in the US, he had citizenship from another country that the US government currently did not like. So, the men with sunglasses show up in my office and say, oh, you're working with a foreign national. How are you ensuring that he's not taking the code or the algorithms from your project and passing them on to his home country, to people that our government currently doesn't like? And I just looked at them and I said, well, I certainly hope that China has all of the air traffic control protocols we're working on. Because China lands planes in the US. So if China doesn't know how air traffic control works, we have bigger problems, right? And of course, the men with sunglasses are trained to not crack a smile, but I don't know how they did that. This is the kind of thing that we run into all the time, right? A lot of systems in aerospace only work if everybody has the code or if everybody knows how the system works. So we have the more difficult cybersecurity problem of how do you ensure that access so that the system works, and how do you also secure it? And of course, this doesn't just happen to planes, right? It happens to spacecraft too. I'm saying aerospace. Here's an article from spacenews.com where Boeing was implementing more rigorous testing of its Starliner after software problems appeared there, right? We can see in the caption of this figure, it says that the CST-100 Starliner commercial crew spacecraft had two major software errors found in its uncrewed test flight last December. So this happens everywhere and it's newsmaking. It's a big deal. It's expensive. And of course, I'm really not picking on Boeing. This really does happen to everyone. Here's an even bigger catastrophe. This was from the European Space Agency. And in 2016, they suffered a very major loss in terms of the Schiaparelli lander. It was supposed to land on Mars, and instead, a small data glitch happened to take down the entire lander, and the mission ended with the lander crashing at a high speed into the Martian surface. It was a total loss of a time-consuming and expensive mission, expensive in terms of dollars, but also expensive in terms of resources that were put into this project in terms of the data that was lost. And in this case, the software error was so small, and it should have been caught both in the initial software plus in software that hopefully would be on board such a mission to test data glitches, right? When you're sending a spacecraft, a one-off spacecraft on a risky mission to do something no one's ever done before, you're going to expect that at least sometimes your data that you're getting in about your environment might be imperfect or unexpected, right? You might have some sensor drift, you might have some sensor noise, you might have some weird outliers or something that got into a strange state that you didn't expect. It's really, really hard to predict everything that could possibly happen and to test from that and eliminate it from your code. So the flight software needs to be robust for that. And in this case, it wasn't, and it was a major loss. So this is a big problem. It happens everywhere, and we have not at all solved it. Okay, and a lot of it's caused because we're going from this, right? These are hardware planes. These are elite fighters from World War II, and we are going from taking all of their capabilities and turning them into software. This is one of the latest examples of this. This is the F-35 from Lockheed Martin. It has over 8 million lines of code. I think if we were to make a graph, I'd love to do this sometime if I could get my hands on all the data. If we were to make a graph of the amount of software as each plane comes out, the amount of the plane's capabilities that were implemented in software versus hardware, I suspect it would look like an exponential curve, because in this case, we have more than 4 times the code of the F-22 Raptor. Lockheed Martin on their website, f35.com, says, from flight controls to fusing together the F-35 sensor data to form a clear and comprehensive picture of the battle space, software is essential. This plane doesn't run without software at its core. So how do we rise to this challenge? How do we make things like this running? How do we make the plane after the F-35? And essentially in space, right, we are here. This is the International Space Station. And we are already at the limits of what we can do in the state of the art, right? This has been a tremendous success in terms of an international collaboration and in terms of moving capabilities to space, but we also struggle with a lot of real software problems. I saw a wonderful keynote by one of the leads of the International Space Station at the NASA Full Methods Symposium in 2019, where she was talking about how, just like hardware, when software gets to space, it gets used for whatever we need it for, right? So systems that were built or intended for one thing might be used for something else entirely. They might be repurposed because a new need came up, or there might be a change of plans because, again, this is a large international collaboration. It changes, it evolves over time, right? We start building something and then we come out with a new technology and we upgrade it. So our systems need to be adaptable and scalable and repurposable, and we run into problems all the time just in the current day that we are really struggling with how to handle. So if we are here, then how do we go to here, right? How do we go to the future that we envision, where we have these deep space outposts where many vehicles can dock around the edges and they can go on missions? There's an international collaboration right now between all of the partners of the ISS, right? NASA, the European Space Agency, JAXA, and others to build a gateway, which would be the first prototype toward such a deep space outpost, and it would enable the Artemis mission to the moon and to Mars. And so how do we scale that, right? And if you're a Trekkie and you watch the series associated with my graphic here, you'll notice that Star Trek conveniently smooths over how they solved 3 major problems in the universe, right? Hunger, world peace, and software. The first 2 are outside the scope of this talk, but we can take a crack at how we might possibly get on a path to solving the 3rd one. So looking at the state of the art, maybe the first thing that we ask is, well, what regulations are there? What guidelines do we have that might tell us how to go? What's our ideal path? Well, there's a survey that you can see I linked at the bottom here that talks about regulations, what exists today and what's in the works for all different kinds of software for autonomous systems, including specifically flight software. And the answer is, in terms of flight software, as well as the rest of the field, there aren't all that many. They're all on this slide. Of course, we first have the RTCA, that's the Radio Technical Commission for Aeronautics, their document DO 178B and 178C. Those are for software considerations in airborne systems and equipment certification, and they were supplemented shortly thereafter with DO 333, that's a formal methods supplement. None of these are short. Okay, the supplement is 118 pages, and they're also not readily accessible, for example, online. You can't just go to Google Scholar and type in DO333 and have 58 versions come up that people have posted publicly everywhere. They're a little more difficult to get a hold of. You'll see a lot of expensive classes about how to read and interpret them. The short version is they don't fill in the guidance that we would like. They don't give us the standards that just say, here's the way, and we have a solved problem, right? They do put out certain metrics that we need to meet in order to be able to fly something. Like, for example, the probability of a system failure for a critical system needs to be 1 in a billion. Basically, 10 to the negative ninth per flight hour is how they put that in these documents. But of course, they don't tell us how to do that. They just give us suggestions. And even once we figure out paths to do that, we have questions about, like, who checks the checkers? How do we verify the verification engines? And what sort of standards do we need to meet for our verification engine verifiers? There's relatively little guidance on that too. There is a NASA software engineering requirements appendix D on software classifications that gives various classes for different kinds of flight software. In this case, class A is the most rigorous, and it's quite difficult to achieve software that fits into a class A certification. It has to be very rigorously verified. And at the moment, class C encompasses all, quote, software used to verify system requirements. It's not entirely clear whether that means all ways that we can verify the verification engine. It's not clear whether maybe in the future we need some different regulations, but depending on what kind of verification we're doing or what kind of system we're verifying, right? Do we verify a system that maybe includes learning or non-determinism a little bit differently? There's not a lot of direction here, and importantly, this is a hard problem. I love this paper here, the infeasibility of quantifying the reliability of life-critical real-time software in the context of flight software, written by 2 experts at NASA Langley Research Center, and they lay out exactly why this problem is hard and exactly why these guidelines give us just enough to make the problem really, really hard, but not enough to have a path to be able to solve it. So how do we go about figuring out how to meet these regulations? Well, we need methods, we need algorithms, we need tools that implement those, we need these to be available, and we need them to be non-academic, but we need them to be industrial quality and affordable. We need training, automation. How do we make this process so that it is not onerous and it doesn't take too much time and effort, but actually fits into a reasonable development life cycle? And then how do we drive future standards or processes so that things fit together, so that we have a way forward, so that we have some kind of method? There are a lot of standardized methods for software engineering, but somehow software engineering of flight software, it has very few compared to the rest of this field. So how do we fill in that gap? And there have been some really wonderful ongoing efforts to start chipping away at that. One of them is the software verification competition, SVComp, and you can see the link to the next SVComp here at the bottom of my slide. This is a competition for the state-of-the-art tools for verifying pieces of code using software model checking. So the most exhaustive form of code verification that we have at this moment. But even though SVComp, which has been running for many years and has a very well-established machinery for evaluating tools and has driven a lot of competition, and it has spurred tremendous advancements in these tools, it's still not matching up with where the systems are that we might want to verify. For example, the largest one of the C modules in their benchmark suite is only about 80 kilobytes or 44,000 lines of code. And notice, for example, the F-35 I showed you earlier, which was over 8 million lines of code. Of course, we would ideally not verify that all in one go, right? We would do that compositionally, we would divide it up, but still you can see the scale is not quite comparable. There are only 2 programming languages that SVComp has tracks for currently, C and Java. So other programming languages, we're not as good at. And in Java, the largest Java module is only 32 kilobytes, or about 1,200 lines of code. So again, not quite comparable to real programs. And importantly, this code is pre-processed so that library code is actually included in the benchmark. So that makes this code even smaller, because this isn't how many lines of code a developer, for example, would write and then include a whole bunch of libraries that allow you to call other things. This is the whole code, including the libraries, okay? And these tools are wonderful in that they output one of three answers. So they output either that true, whatever specification we wanted to verify over the code benchmark module is satisfied, and a witness that shows that there is no violation. That's incredibly useful and the outcome that you would want for any piece of code you verify. But there are two issues here that are not completely solved. So firstly, how do you know this specification that you put in is really going to encapsulate everything you needed to know? How do you know that's correct? How do you know that's what you wanted to say? And also, we don't have a whole lot of engines that can check witnesses. So it's a hard question. How do you prove the absence of bad behaviors to another person, for example? How do you have an automated piece of code that can produce a witness or take a witness and then show that in a way that's explainable to humans? There are several witness checkers that are under development. You can see them on SVCOM's website, but that's a hard question, and it's an active area of research. Also, a tool in this competition, for example, could say false and have a witness. That means the specification is violated, and the witness shows a violation of the software. Or we might have an unknown result, that the tool cannot decide whether the specification passes or fails, or it crashes, has a timeout, has a memory out, whatever. That happens, unfortunately, more often than we would like. So how do we grow software model checking and tools competitions like SVComp to be able to analyze things like the F-35? And importantly, how do we tie these in with other verification tools and methods? Like, how do we complement this with static analysis or other potentially semi-formal methods that allow us to explore code? How do we have a comprehensive tool framework where we can say, okay, let's say I have a piece of flight software and it's written in C. How do I sit down and have one available tool chain that enables me to round off, include pre-processed libraries, etc., so that I can model check what I can model check, that allows me to run static analysis, that allows me to tie this into software testing? How do I do that? There's currently not a way to do that, but that would be really great. There's also been a push, and this is a wonderful line of research that's, again, not quite there yet, but it's a very interesting push, to do software generation from certified artifacts. So the idea here is to verify algorithms, not code, or maybe you would verify algorithms and code. I'm not quite sure which one that should ideally be. You could generate code, for example, from various verification engines, and several popular verification engines have extensions that at least partially do this, if not fully, and these are growing all the time. So you can see my ... because this is a growing list. But for example, new XMV, Spin, TLA+, PBS, these are all engines that have been used to verify real flight software, and all of these are capable of generating C code, which is arguably the most commonly used language for flight software, from a verified code engine. But then how else do we train software engineers? So our current education, both at universities and at companies for software engineers, does not include this process that I'm showing on this slide, right? We're more used to a process where we have requirements in English, or maybe we have requirements in a tool like that allows us to draw state machines and play with them there, right? We don't have requirements in new XMV. generally in software engineering training. And we don't have a process for here is the smooth way to take those requirements and then translate them into something that one could verify for flight software and carry that through the rest of the system. So what does that look like? What do we train people to do? And then of course, how do we maintain this? Because if we've generated the code, we still at some point need to go back in and modify that, right? Does that mean we have to regenerate it? But what if it's hooked into other things? Clearly, people need to be able to interface with this at some point. We still have other ways that we need to validate that we captured what we intended to capture. So this all creates a large problem for maintenance and traceability over the years. So that leads to some of our biggest challenges going forward that I wanted to highlight in this talk. And one is whenever we're talking about formal methods or pretty much any verification technique, but especially formal methods, they're famously garbage in, garbage out, right? So if you want to perform model checking, for example, there are two required inputs to model checking. One is that you need some system model. You need some description of your system in a formal semantics. That could be the code itself, or ideally, it could be something that is maybe a partial design, a design so far from very early in the system lifecycle. You need that. And you need that in a way that is formally analyzable, which is maybe different than how trained software engineers might be used to producing such a thing. You also, and this is even harder, need verification specifications. What emergent behaviors do you expect to hold over your system? And those are really hard to write. They're especially hard to write when you haven't fully mapped out the system yet. And of course, then your verification result is only going to be as good as your inputs. So you have this very tenuous connection here where your inputs to formal analysis are the biggest challenge, and you really have to get those right in a universe where we're not trained to do those effectively, where this isn't part of an established process. And specifically, just the question of where we get specifications from is very hard and an unsolved issue. This is arguably the most time-consuming part of any verification effort of software, especially one that might integrate informal methods like software model checking or static analysis. So we have the problem that a lot of safety-critical systems are initially designed without at least what the formal methods community would consider to be formal requirements. There are a lot of times much more informal requirements, and we're used to dealing with things like that. We're also still seeing many places things like the V engineering model, where we have a software design process that doesn't either define requirements or doesn't refine requirements to the level that we could actually use them for verification until way late on the other side of the V, until we get to some testing phase. And of course, that doesn't fit with the process that I highlighted earlier, where maybe we define the requirements first and then generate the software from them. If we're used to doing this in exactly the opposite direction, that's the problem. We need to change. And also, when we try to write specifications early, when we try to fit into this process, we end up with specifications that mix many different objectives. So if you sit down and you read an aerospace operational concept, for example, where you have a large panel of experts in the field mapping out what is this system supposed to do, what's the whole operational concept behind this thing that we're about to build, you'll see all over the place that they're mixing levels of detail or different levels of abstraction. And it's very hard to separate those out and say, okay, we're going to have all the specifications at this level of abstraction or that level, or maybe both levels, and how do we pull those out? They also mix how the system is defined versus how it should behave, the emergent behaviors that they expect to see. Right? So one of the most difficult tasks, for example, in creating those inputs I highlighted on the previous slide for model checking, is which bit of the sentence, maybe it's the same sentence, goes in the here's the definition of the system model, and which bit goes in the here's the emergent behavior I expect to see part. especially because your whole design for the system is meant to produce the emergent behaviors that you want. So there's a really good reason why they're mixed, and then separating those out, especially separating those out in a way that gives you meaningful results for verification, is incredibly difficult, and we don't have a well-defined way to do that. They will also mix in legal speak on why the system satisfies certain rules. That's an important consideration, of course, but it's also really hard to separate out to get clean specifications. And also you'll see mixed in the desires or opinions of the designers, right? You'll see things about usability or environmental impact or future features or options, or that the interface should preferably be blue, or all kinds of extraneous details that maybe aren't relevant to the specifications you want or the level of abstraction that you need to capture. So this is a really hard problem. In fact, I have an entire paper in a former keynote talk on exactly how do we map out this problem. And of course, whenever we go to start a big project, we end up with a big roadmap that looks like this, right? So you start the project. I just started verification of a new project in collaboration with a team from NASA. The first thing we have to do is ask the question, where are we now? And there isn't an obvious answer, right? What tools are available that are amenable to the kind of system that we're building? What is the current status of those tools? Will they give us something that meets all of our certification objectives? Will we be able to use them in a way that doesn't require this huge learning curve only to figure out, oh no, that didn't actually do what we wanted? How robust are the tools? What's available, and what are the interfaces, and what can we hook together in a realistic chain, right? So we have to reassess that at this point every time we start a new project. And that's not a standard thing for all other types of projects that one might start, right? Usually there's more is known about what kinds of tools and resources are available, or what kinds of processes are possible. And in this case, we don't have that to rely on. So then once we know where we are, what's the shape of what's available for verification, in particular for the kind of system that we're dealing with, then we have to answer all those questions I just talked about where do we get the specifications from? How do we write them? And then once we write some specifications, we have this very important question of, how do we measure specification quality? How do we know that we have enough specifications, that we covered the things we want to cover? How do we measure coverage? How do we know that all the specifications can be true of the same system at the same time? How do we know they're not over-constrained or under-constrained? How do we know we don't have conflicting or vacuous or otherwise possibly incorrect specifications, especially when we try to formalize them, like in a temporal logic, like linear temporal logic is a popular choice. It's amazing how easy it is to write an LTL formula that doesn't quite capture what you thought you meant in the English. And that's true of people who are experts who write these all the time. So especially if you take someone who is a system designer, who's maybe not a specialist just in writing specifications, but in designing this whole kind of system. How do they know that they've written quality covering specifications that capture what they need to capture about their system to make verification meaningful? And then how do we best use these? How do we use specifications in a way that we can explain to humans, that we can integrate them into safety cases, that we can hook them up compositionally to create a case for a whole system? How do we write specifications and store them in some way that we can, for example, use them for early design stage verification, and then tie that into testing, and then tie that into runtime verification while the system's running? And how do we organize all of this? How do we keep track of, well, here was the English, and here was where that was from, and here is maybe the temporal logic or some other formalism or the code that represents that, right? How do we hook all of those together? How do we hook them together in a hierarchy of abstraction? And how do we keep track of this, organize it through the many stages of development and then later maintenance of the same software? Aircraft fly for over 30 years, right? So you're going to have this thing that's in the air that's in operation for a really long time, and you have to have an organization scheme that's going to hold up over all those years, over many different people who are updating this and upgrading it. So how do you build something like that? It's a huge unsolved problem. And then once we solve the specification problem, right, once we just get the inputs, the next challenge is connecting the dots to all of the other stages of the system, right? So once we have specifications we can analyze with tools, we run into the problem that the current tools don't scale to analyze real systems. And we just saw a highlight of this when I showed you how big the benchmarks are, the benchmarks for stressing out tools in SV Comp versus how big the code is for example, an aircraft that's flying right now, right? We need our tools to be able to keep up in this arms race, to be able to analyze systems that are as large and as complex as future pieces of software are going to be. Also, a lot of times the tool chains don't start in the real world, right? So they don't start from a place where people are writing these specifications and debugging them and changing them. A lot of the tools that you read about in academic papers start with this assumption that there is a perfect set of specifications written on tablets left on a mountaintop by God, and now we can just use those conveniently to show that our tool does amazing things. And that's wonderful that the tools do amazing things, but that first part is really not realistic. So how do we hook up the beginning of these verification engines into what specification really looks like in the real world? And the tool chains we have now also end prematurely. So for example, we have two kinds of code generators that are available out there. We either have the sort of Simulink type code generator where maybe you have this great tool that maybe seems very intuitive to you, where you can design a system perhaps as a state transition diagram, where you can debug your specifications, and there's this convenient button to hit generate C code from this, and then you get C code that is generated that is large and bloated and slow and completely not human readable and impossible for a human to be able to maintain. And even if we could come up with a human to maintain it, we would first have the insurmountable hurdle of how do we make a reasonable argument from that piece of code that we know that it represents whatever formalism we input, that we visualized, that we did some verification over. How do we have traceability? A lot of these code generators are buggy. Where does all the bloat come from? Flight software is, of course, real-time software most of the time. So there's a big argument for, do we really need that? It starts looking spurious very quickly. Then we also have the other type, like for example, the PBS model of generating code. So there's this wonderful verified code generator that takes artifacts from the theorem prover PBS and generates C code from that. But then this is going to be smaller than your whole system code, right? So you have the Goldilocks problem of either too big or too small. So if you use this model, you're going to get some very small, probably very human readable and easy to validate code, but it's not going to represent the whole system. So you still have to have a significant amount of humans adding to the code, and then how do you verify that whole conglomeration? Now you don't just have the code generated from the artifact that you have proven correct in your trusted theorem prover, right? So the tool chains don't carry through. There's also no standard interfaces for tools to hook up to each other for compositional verification or for creating a safety case over the whole system. There's a bunch of standalone tools and they all have different interfaces, different inputs, different outputs, and there's not a standard way to hook all of these things together. And this is actually also especially the case for runtime verification engines. Going into my last bullet here, I think every single different tool that purports to do runtime verification that is currently available has a different input interface. So not only can we not have a competition that we compare these tools, you can't have some kind of standard tool chain where, and then you have data in this format and you can just run runtime verification over it, right? It all looks completely different. So you end up with whatever tool chain that you string together from picking up various tools for different parts in the system design lifecycle. You end up writing a lot of translators. And then you ask questions like, is this worth it? How do I know my translator is correct? How do I know I'm carrying through things the way I intended? So this isn't as easy as we might like it to be. And then even when we plan ahead and say, we're going to do this right, for example, I'm going to design a system that, for example, incorporates runtime verification from the beginning. So rather than the unfortunately more common scenario of, oh crud, the plane is flying and it has a problem. Can we put runtime verification on there so we can detect this problem and then do this trigger because we know this problem is going to happen over and over? Instead of that, maybe we're like, okay, we want to prevent all of these things, so we're going to design runtime verification in the beginning. Great. But then how much resources do we need? How much space, how much time, what kind of hardware, what does that look like? If I want to runtime monitor this many things, or my specs look this way, what does that look like? No existing runtime verification tool is packaged with some kind of resource estimation engine that allows you to answer these questions up front. And they're important questions. There's also not tool chain integration that allows you to, for example, carry all of your specifications. We already established specification is the biggest bottleneck. You can't carry specifications in currently from design time or from testing. So we have a lot of challenges in terms of connecting the dots. Also, I think it's rather telling that 2 of the last 4 covers of Aerospace America, that's the professional society magazine for AIAA, 2 of the last 4 covers have had aerospace cybersecurity as their topic. I don't know that this is going to be a running trend, that it's going to be half the covers of the magazine from now on, but you get the point. This is becoming an increasingly urgent and pressing problem. And we have things here like on the left, protecting the International Space Station. Given NASA's troubled cybersecurity record, experts urge fresh attention to the station's cybersecurity. Well, of course, the ISS, as we covered, right, is a large international collaboration. A lot of things only work if everybody has access and everybody knows how they work. And of course, one can imagine it's not an easy thing to get a job in software engineering or cybersecurity at NASA. We're talking about a very elite group of highly trained professionals, and they still have trouble because it's a hard problem. So how do we solve this, right? And then over here, we also have your new cyber allies working with instead of against gray hat hackers to try to solve these problems. We don't know how to do that. How do we incorporate in cybersecurity? How do we grow it to being able to reason about flight software, and importantly, flight software that we can still get flight certified? So here's a summary of some of the major challenges that we have ahead in order to achieve a sustainable, scalable schema for future avionics. We have to solve challenges in specification, in tools and algorithms for verification, in planning and integration, and culture of integrating these in, and of course, cybersecurity. So that's what we got to do in order to boldly go where no software has gone before. And I'm happy to take any questions.
Thank you so much, Kristen. That was an excellent talk. And now we're in the Q&A phase. So if you have questions, you can either type them into the Zoom chat or the Clouder chat. And to kick things off, I'd like to start with a question specifically from your perspective, what emerging or maybe even existing programming language technology do you think might have the most impact potentially going forward on the aerospace domain?
Do you mean in terms of having a new programming language, or what is the context of your question?
Sure. I think even from a new programming language perspective would be interesting, or even maybe even existing programming languages, do they really fit in this domain? So for instance, we've had real-time Java for a very long time. There have been some projects from the OVM group with Purdue in collaboration with Boeing that put him on the Scan Eagle UAV, and there's some efforts in the EU with ICAS and the Airbus, I think the engine control module, but we haven't really seen kind of like a pervasive adoption of languages outside of like Ada and C in the aerospace domain. So I'm just curious about your thoughts about, you know, how programming languages can really fit into the aerospace domain.
Yeah, so I think that's a very difficult challenge because on one hand, like I said, planes fly for 30 plus years. So whatever you do with new languages, you're going to have to also do with C, for example, because you're going to have this decades long lag time between, even if you created a new language or a new technology, a new pipeline for here's the way to do flight software, you're going to have this long pipeline and major cultural barriers to integrating that in. And in the meantime, you're going to need to be able to make those same kinds of strides with the existing software whenever you do upgrades or maintenance. And the existing software is largely in C. And it's maybe not the best choice of language, but it is what it is, right? So that's where the software is now. And any new solution would have to be, of course, real time. It would have to be as faster than C. Clearly, there are some things that would be very desirable, right? Like making this more straightforwardly verifiable, having different kinds of checks built into the language. Those would all be really nice. But then you have these other cultural barriers in terms of education and training. Imperative languages are the first ones we tend to learn. Some universities start with Scheme or something like that, but in general, we start with imperative languages. Certainly in aerospace engineering programs, it's usually imperative languages. It's usually C that's the first language, sometimes Python, but still that sort of mindset. So how do you take, for example, a lot of flight software is actually written by aerospace engineers, not trained computer scientists. How do you take languages and constructs and make them appeal to and be sort of easily integrated into the training, education, and processes for aerospace engineering, as well as for computer science? It's a hard gap to bridge. And I think maybe one thing that a lot of the software engineering community doesn't think about, maybe as a first pass when they consider such a problem, is that this is going to be something that actually predominantly maybe won't be used by computer scientists. So how does an aerospace engineer think? How do they get trained? How are they going to use this? How do you design something for use by an aerospace engineer, not a computer scientist?
All right, thank you very much. So we have another question. And I'll read it to you. There are big people issues in software development for critical domains: team organization, training, evolving practices, and tools. Do you see benefits and/or problems with younger developers who are trained in agile development techniques?
I wouldn't say problems so much as challenges. There are a few things we can take from Agile that work really well in aerospace engineering, like the standing meetings, that tends to make people get to the point. But definitely, if you are looking to do this kind of flight certifiable, rigorous verification, definitely the timeline, the push to just getting it done, the sort of philosophy of Agile seems quite opposed to that. And I know that there have been a handful of papers here and there, right, that try to marry the two sides, that try to take some of the benefits of the Agile process and also integrate in some of the rigor of verification. And that's wonderful, but it's not quite far enough, right? So especially when we're talking about flight software, we're at the far end of this really needs to be rigorous, right? Tiny bugs in, for example, a piece of software that might process payroll for a company, or that might do some everyday function on your phone or whatever. A small bug in something like that might be annoying, but it's not going to make the headlines the way that a small bug that still doesn't even kill anyone, that doesn't do anything, does in flight software, like those headlines that I showed at the beginning of this talk, right? So the kinds of things that are acceptable in the Agile process are not acceptable in flight software. And I feel like that has created a challenge for a lot of people that have been trained in that process of, no, we really need to do things in a really fundamentally different way, because we can't afford to let those things slide. It's a different mentality and a different end product, and you don't have the same kind of safety cases that you have to construct at the end of an agile process that you do to apply for flight certification, for example.
All right, so we have another question. Could you talk a little bit more about runtime verification and how it might fit into maybe a modified V&V model if, for instance, we were able to solve the kind of software verification problem? Would you still see a benefit to runtime verification being deployed in a system?
Oh yes, you always need runtime verification. And I have some examples as to why actually. So let's see, I'll skip through this one. I think maybe the Schiaparelli lander is a really great example. So you're always going to get things that you don't expect or that you couldn't possibly anticipate, right? That's going to happen no matter how well you formally verify your software. And so while runtime verification will not fix your software, it will help your system be resilient to the things that you couldn't know to fix your software to be robust to. And in this case, we're giving the benefit of the doubt to the ExoMars lander, right? This was in October 2016, and to give you the context when this bug occurred, this is the lander. It was about 12 kilometers, 7.5 miles above the surface. It was going quite fast, over 1,100 miles per hour, or over 1,700 kilometers per hour, and it correctly ejected its heat shield when it was almost 5 miles or almost 8K above the surface. And then what happened, the data glitch that they were speaking about in the article I showed, was that the IMU miscalculated this saturation maximum period by 1 second. So that was the data glitch, right? Problem with the software. Okay, that happens. Why did this cause a crash? Well, because then that value was used by the navigation system, and that led to a failure where it calculated a negative altitude, despite the fact that it was almost 5 miles above the surface, definitely not below the surface. And that triggered a premature release of the parachute and back shell, a firing of the braking thrusters, activation of on-ground systems at 2 miles above the surface. And of course, by the time you've done all that, a crash is inevitable. So let's say that we want to integrate in runtime verification into the system. There are a lot of places where runtime verification could have been integrated and where it could have been helpful to this software system. So for example, we could runtime verify a set of sanity checks that are relevant to this mission. And some candidates could be, we could have a RV module that monitors for that while you are in descending toward the surface mode, your altitude can't be negative, right? This is an easy, fast, real-time sanity check. We're not having a repeat of the implementation of the software, like we're not running a parallel version of the software, right? We're just saying, here's a sanity check. I don't know how you got a negative altitude, but I know it's wrong. So I'm going to trigger something else in the software to say like, yo, hey, we need to reset this. We need to use something else. Similarly, the rate of descent can't be faster than gravity, right? This is a quick sanity check that runtime verification could independently monitor for, and it doesn't matter why or how the software got there. We can fix that another time. We just need to know that this software is wrong here, and if it knows that it's wrong, then we could trigger the appropriate mitigation action. Also, we could have something like the change in altitude must be within normal parameters. So there is no Scotty in this scenario. You cannot be beamed from 2 miles to below the surface in one time step. And importantly here, the saturation maximum had an a priori known temporal bound. And that's important for a couple of reasons. Firstly, because we could create a runtime monitor to just check, hey, we're calculating this thing. Does it make sense? Is it in the realm of possibilities of what we would expect to get for a right answer? If not, we have a maybe not perfect, but a usable alternative answer stored here, right? So one thing that ideally could have happened if we had been running a runtime monitor on this lander is we could have gotten that miscalculated saturation maximum period. The RV monitor could have gone off and said, hey guys, this is not within the bound. Let's use the pre-calculated one. Maybe we're off by an eensy-weensy bit. We knew that could happen anyway, but if we use the pre-calculated one, we're guaranteed to not be off by as much as whatever that thing is. And then if they had used the pre-calculated one, my understanding of the post-accident report is that would have prevented the crash. So they could have just filled in this alternative value. In fact, they, in any of these cases, right, if they had had a runtime monitor for some scenario that maybe they didn't anticipate or couldn't have anticipated, that their calculation could have been messed up by something, they could have triggered, all right, let's go to the safe path here and let's implement that. And then we know that we're going to be able to land this. So because we'll never be psychic and the environment will always throw things at us we didn't expect. And if nothing else, we'll have the International Space Station problem, right? Where even if you design software that perfectly handles all of the cases that it was meant to handle, right? You're given a requirements document, your software has to handle all these things. Even if you do that perfectly, you send it to the ISS and someone goes, here's a tool. It looks like it would do what we want, right? Hardware, software, doesn't matter what it is. When you're in space, you use the tools around you. So your software might be repurposed to do something else. And now suddenly there are things you couldn't possibly have anticipated. And it's amazing how people come up with ways of using tools, right, when necessity drives that need. And having some kind of runtime monitor that can just very quickly say, okay, this is clearly not going to lead to the right path in the software. We need to go to the safe path over here that's maybe easier to verify. That's always going to be a valuable tool. Does that answer the question, hopefully?
Yeah, that was wonderful. Maybe just a very short follow-on question, and I know there's a bunch in the chat that we'll get to soon. So in your example, you relied on having some pre-calculated values that you could fall back on. Would you ever envision a system that maybe had like either a code generator or a compiler as a part of the deployed system, where instead of just relying on some pre-generated value, we might envision maybe synthesizing a new component that might correct for the behavior? Granted, in this case, it might be impossible because it sounds like there's just not enough time, but maybe in other instances that might we might have enough time. Do you think that is a possibility or even a valid scenario?
Yeah, we've talked about this when we're talking about, for example, how to verify, maybe you have a rover or something, it goes to another planet. Well, all right, it's a real-time system, but it still has lots of time to, it sort of does a couple of things for the day and then it, rests and let its solar panels recharge and things like that. And so these aren't running at quite the speed of something that's descending very quickly toward the surface of a planet, right? Once it gets on the ground, it might have time to observe that, okay, I need something to handle this scenario, or maybe it even synthesizes that will need some kind of part and has a 3D printer on board and can manufacture that or whatever, right? Ideally, we'd have these really great, maybe partially non-deterministic learning adaptive systems that could do things like that. Yeah, and then that presents a whole bunch of other questions of like, what does it even look like to verify those? Having sanity checks maybe becomes even more important. So for example, if you are learning or adapting or compiling something or coming up with something, one really great way that I've hypothesized, I've never seen anyone do this yet, but I would hypothesize that runtime verification, sanity checks would be a really great way to guide those kind of processes. So maybe you're running runtime verification in parallel as like a sanity checker and you don't want to learn something outside the box, or you don't want to synthesize or compile a piece of code or compose something new about your system that violates some known property about what would be acceptable or what would comply with the physics of the situation you're in or whatever. So that could certainly be used to make something like that more efficient.
Thank you very much. So that kind of leads into another question, which was asked, which is right now, machine learning is super popular. But this area seems like an opposite of the rigorous software that's used for the development and verification of airborne systems. Do you see any good applications of machine learning for aerospace systems?
Yeah. Oh, there are tons of good applications. It's just what does it look like to be able to verify those? What does it look like to make assurances? And that is a huge open question that I don't have a lot of answers to. So in the paper that I highlighted early on in the talk, and I think once I go back out of my appendix here, I might be able to click back on that. Yeah, so in this paper here, right, we talked about different levels of autonomy and systems that are able to learn, and sort of how do you classify that and what do regulations look like? And the answer is they don't look like much of anything at the moment. And so then we sort of foray into what should regulations I aim to look like? What types of things do we need to regulate? That is a huge open question of yeah, how do we maybe start with boxing learning so that, okay, maybe we have the core systems, like we were looking at the software in the aircraft in the articles at the beginning of this talk, and things like delivering the correct altitude and attitude and stats on engine operation. That part really needs to be proven to be running in isolation in a very robust way so that we always know that we are operating on the correct data and that the core operation of whatever safety critical system, in this case a plane, is preserved, right? And then of course we would love to have a future where then we can learn things, right? Like maybe an unmanned aerial system is, we can prove that its core operations, its core safety critical operations are preserved, but then it could maybe have an option to learn that the human passenger, if it's urban air mobility, right, it might have a human passenger but no pilot, and so maybe it learns to take the more scenic route, or it learns to recognize when a person is ill, and then it would deviate to a hospital. Like maybe the person is ill enough that the person can't call for help or something, or passes out, has a heart attack, gets incapacitated. How could the UAS learn, like, well, I have someone in need on board and what do I do with that? Or learn, okay, well, when I pass through this area of town or something, there tends to be wind events because of the shape of the buildings below or things like that. How do I get more efficient at dealing with that each time I pass through, so I can plot a better flight path and I can preserve fuel and be more stable, right? We would love to add in learning for all kinds of interesting things. And then there's a huge amount of questions as to how do we separate that? How do we verify that? What does verification look like? Does verification for that need to be as rigorous as it is for the core systems? What do the regulations look like? And of course, we don't have any tools, algorithms, much less tool chains or industrial processes to handle that. So that's a great question. I look forward to seeing what research comes out on that.
So I have a couple of questions that I'm going to combine together because they're related. So what is the state of the art of applying formal verification in real world flight programs such as Boeing, Airbus, or NASA? Do they scale to large scale software? And what do you think is the most used verification tool in the field?
Wow. So that's a lot of parts of the question. I'll break it down. There are several tools that are used in the field. And of course, it's formal methods with an S, right? Because there's not one method that provides a silver bullet for everything. And even when you find one method, there's usually not one tool that has the most usable interface, for example, for the way that your system is specified, the way that your system is being engineered. Usually there's an input language that fits better with the type of system that you want to describe or what have you. So there are lots of tools. Some of the ones I highlighted in this talk, of course, PVS Theorem Prover is used a lot at NASA Langley for verifying all sorts of different flight control algorithms and systems. I know Boeing and NASA also use, for example, new XMV. Spin was, of course, famously created by Gerald Holtzman, who was at NASA JPL until his retirement recently. And I have been on projects at these places that have used, for example, TLA+. So there are several different tools that are used for verification. And again, it depends on the kind of system. I think you can say that all of these tools have the ability to verify some full-scale real-life systems, but we are not anywhere near the capability to verify all full-scale real-life systems. And in particular, we know that any system anyway is going to need to be verified compositionally. These are very large. And I told you things like the F-35 is more than 8 million lines of code, but it's not like we would expect to run one software model checking instance on the 8 million lines of code and be like, okay, check, it's verified, right? We would expect to run software model checking maybe on just this little subsystem or just this module, right? So how do we break up the systems? How do we have an interface? I've been on a project, an industrial project recently that was using assume guarantee reasoning so that each submodule of a larger system and then sometimes each part of a submodule would have some kind of assume guarantee contract. And so then the idea was for the system designers to break off each part that they were designing into a set of interface assumptions and then guarantees of that part, and then use that in driving the selection of whatever verification tool or method they were using. So when we have a very concerted effort like that that goes on, it becomes achievable to get pretty far. But it's still a lot of assessing, okay, where are we now, right? In terms of what tools are available. I know now that I have this small bite-sized sort of chunk of something that would be reasonable to verify. What tool will work from that? How do I get the inputs I need for that tool? Once I verify it, how do I hook it to the rest of the system? How do I use this interface? Maybe the other parts of the system that I'm interfacing with were verified by different tools. So how do we bridge that gap? How do we hook everything together? And how do we translate that into a safety case that we can say, okay, this whole system is safe now because we verified the high level architecture this way, and we broke down each of the lower components this way, and then we can build this into a nice compositional argument that we could turn in for flight certification. People have done that. People do that for each new project, but there's a lot of charting a brand new path every time. So the state of the art does not include a standard way of doing that. And I would say we're not close to a standard way of doing that. Each system that's developed, each system I've seen in an industrial context has had a different path. And I would say oftentimes of the projects I've seen, there have definitely been parts of the path that were not as formal, or people couldn't find a path to achieve quite the verification results that they wanted or needed. And so there are definitely a lot of challenges for methods and tools to verify pieces of systems that are particularly hard to reason about.
Thank you. That was great. We had a follow-on question about runtime verification. And specifically, we were wondering whether the sanity checks that you were talking about, are those injected primarily by the programmer, so via manual programming, or do tools exist that would either identify where those checks might be, should be added, or even generate the checks themselves?
Yeah, so that last part, that would be awesome. And we totally don't have any tools that do that. So currently there are no tools that figure out where these checks could be, or much less automatically generate them. That would be amazing. I would settle for just, well, if we did some kind of verification, like design time verification or testing, like how do we take the artifacts from those earlier verification stages and then use those to generate maybe the input for a runtime verification engine. That comes with a lot of problems, not just the interface problem of how do we get two things to talk to each other, but also if you think about it, there are a lot of times necessarily different levels of abstraction involved in maybe early design time. Checking might be at a higher level of abstraction. Like I want to know, does the overall architecture or the algorithm for this work, right? Whereas runtime verification is going to be somewhat at a lower level of, is the sensor working? And that by the time we're to runtime verification, we're also looking at a slightly different question, right? Because when you're verifying a system that you have not finished building and started flying yet, you want to know not just what doesn't work the way you expected, but you want your verification engine to give you some indication as why not, right? Because you want to be able to fix that. And runtime verification, on a real system anyway, necessarily has a different purpose, because by the time the plane is flying, you don't really care why the software failed, right? You want to not kill anyone on your way down when you're realizing that you are crashing. Figuring out the why is not going to happen in real time. You're not going to figure it out and fix the software and miraculously save the air. That's not going to happen, right? And so runtime verification is about what is the most fast, efficient, instant way to figure out, is something wrong? If yes, fix it, right? Trigger the mitigation action that would possibly make this better, and we can figure out why it went wrong later, right? Before we fly the next mission. So, and where we run into some problems is that actually, I would say the majority of research done so far in runtime verification is a lot answering the wrong question, at least when it comes to flight software. So a lot of runtime verification tries to hook into those early design questions as to not just did something go wrong, but do fancy diagnostics and prognostics. And all that stuff is very computationally complex. And you end up having these theoretical tools that could tell you, hey guys, you know, your UAS had this problem and it miscalculated this and it crashed. And it tells you that 3 hours after the crash, which, okay, but not really useful. So yeah, how do we generate just the sanity checks? That's a great question. I have some theories on that. I have some theories on how we could maybe take some properties that we know about systems. You know, all sensors come with data sheets. All of a certain type of system come with certain properties, right? They're operating in the same physical world. We have some overlapping situational common sense characteristics of the environment. Maybe we could come up with a common way of capturing those. So that would be really great, but those are not solved questions for runtime verification. Does that answer all the parts of the question? Did I miss any?
I believe so. All right, so we also have a follow-on question from the machine learning discussion, which is around the idea of probabilistic guarantees. And when we look at certifying flight software, can we rely on probabilistic guarantees?
Can you rely on probabilistic guarantees?
Yeah, so is that acceptable, for instance, to like a certifying authority?
Well, so you can see right here, right, is that they want this 10 to the negative ninth per flight hour per flight certification under DO 333. So if you think about it under something like, you know, Monte Carlo simulation that would give you probability, that is a really hard number to achieve. And that's one of the reasons why, like this paper here that I cited as footnote number 2, it goes through all of the challenges of relying on probabilistic guarantees in great detail. I highly recommend that paper. It's really excellent at laying out exactly why this is hard and what we can use from probabilistic guarantees and what we can't. So we can certainly look at probabilistic analysis for making design time choices, and there are probabilistic variations on full methods tools. Like, for example, I was involved in a real life case study when I was a civil servant at NASA, where we were looking at an automated air traffic control system. And we used probabilistic model checking to figure out where we should set certain parameters of should this automated system be in charge or should that one be in charge. And we looked at essentially the crossover point, right, where okay, in these scenarios where it's most likely to go this way, you should have this one in charge. And in these scenarios where it's most likely to go the other way, you should have this one in charge. And then given that we could later, for example, when we pick parts for the system, know the probability of failure of some components, then that chart would give us a really detailed roadmap for what's the best way to lay out our system. So there are definitely roles that are important to play for probabilistic verification, but by the time you're getting down to 10 to the negative ninth per flight hour, a lot you need to sort of make the argument that, well, there's basically a 1 in a billion chance that you had an error in your inputs to formal verification, and then formal verification gave you an absolute guarantee that you don't have any problems. And so therefore, in my very rough, leaving out several details calculation that I'm doing verbally as an answer to this question, there's my 10 to the negative ninth per flight hour. That gets way harder to make when then your output is probabilistic and you need a confidence interval that fits in that.
All right, thank you. So now we have a slight pivot in terms of topics, and we'll go to education, and I'll combine a couple questions here. What should we add to the computer science curriculum right now to get a better chance of having a more reliable critical software tomorrow? And a follow-on question, or maybe a tangential question, which is, how do we get students excited about designing software in such a rigorous way, where most students are still stuck in kind of this hacking sort of mentality?
Well, I'm going to modify the first question a little bit and say that it's not just how do we modify the education of computer science, it's how do we modify the education of aerospace engineering, because so much flight software is written by people with degrees in aerospace engineering, not with degrees in computer science. And there's certainly a mix, but if you think about it, to write flight software, you need this incredibly rare mix of knowledge of how the aircraft works or how the spacecraft works and knowledge of software. And either way, if you get a degree in sort of aerospace engineering or computer science, you have some of the opposite bit that you didn't learn to pick up. But a lot of computer scientists are really not so interested in how the aircraft works or how the spacecraft works. I personally find those very exciting. And so all of my degrees are in computer science, for example, but I found learning things in the domain of how those things work to be very interesting. And that's how I ended up here. But you actually have a huge, huge population of aerospace engineers who then try to learn how software works. So yeah, we really need to revise our aerospace engineering curriculum to integrate in software, good software engineering as a first-class citizen, including the core of algorithms and logical techniques that underlie formal verification, so that we can have a hope of integrating in verification, and especially formal verification also as first-class citizens. I think a lot of that is missing from aerospace, and that there's a lot of here's how the aircraft works and here's how the spacecraft works, and by the way, software, yeah, that's where you type code. So that leads to a lot of the hacking mentality there, and that's a huge issue that we need to combat. And then I think in computer science, you know, of course, in every undergraduate program I've seen, algorithms and data structures are, of course, early in the curriculum core required classes, but I think formal methods is often left out, and it's rarely included even as an elective. I've never seen it included as part of a core required class. It might be I haven't done an extensive study of computer science undergraduate curricula, but at least I haven't happened to see it anywhere. And I feel like it's becoming more and more important, especially as software gets larger and harder to reason about as like a single person, or to reason about with more traditional techniques. We write more and more systems where testing just isn't going to cut it. You know, we have only from testing and simulation the existence proof of, given a certain input, does my system give the output I expected? That's literally only half of the question, right? The other half of the question is, does my system also not do what I don't want? And testing and simulation and traditional verification techniques entirely miss that in whole half of the question. And so far in software, software has been small enough, it has been insignificant enough in terms of a small bug, you know, your phone crashing or something. It's annoying, but whatever. It doesn't kill anyone. It's not really safety critical. We've been able to ignore that whole second half. And I think as we're going forward, as software everywhere gets larger and more complex, ignoring half of the verification question is going to be something that we can't afford to do. So that's going to have to be integrated into the curriculum.
All right, thank you very much. So I had another question for you. So another safety critical domain that's quickly approaching is the rise of autonomous vehicles, and those systems have a lot of kind of computer vision algorithms built in for perception and reasoning about where they are, and do you view certification for those systems as fundamentally different than aerospace systems? And since those systems have kind of as part of their core components these vision algorithms, do you think some of the certification guidelines for autonomous vehicles might then kind of percolate up to the aerospace domain?
Yeah, so this is a really, really interesting question. And I think it's highly related. So you can sort of argue it two ways, right? Some people argue that, like this question seems to be doing, that verification of things like autonomous cars is actually the harder problem. And then I've also heard the opposite argued, that verification of autonomous aircraft is the harder problem because you have exactly the question of autonomous cars, but now you have 3 dimensions instead of 2. Um, which one's easier or harder? I don't know that we have a definitive argument in that, but both aircraft and autonomous cars are going to be equipped with vision, right? And we might need to analyze that in real time. We might need to verify things about it. And that ties in a little bit to the machine learning question too, right? Because we see all this amazing research where we can learn these phenomenal things with machine learning over image data. We can learn to pick out all kinds of really interesting things. We can learn to do very, very precise facial recognition, maybe better than a human could do, or we can pick out that that's Alice and that that's Bob. And then we can also design a special set of sunglasses for Bob to wear that will absolutely all the time convince the software that Bob is Alice, right? So we can trigger these behaviors in vision processing algorithms that in some ways seem to be so much more advanced than how humans process vision, and in other ways they're tricked by these really obscure things that are completely different, right? And one of the really challenging things in certification that is occurring in both aircraft and in ground vehicles is that, how did we certify humans to do the task that we're now automating, right? When we talk about autonomous cars or autonomous planes, what we really mean is, how do we replace the humans with software? That's the question. How do we replace humans with software? And so then we go to, okay, well, what did the humans do? And how did we certify the humans to do that thing? And we have very well-known answers to that, right? We know how humans learn to drive. Humans get driver's licenses. We know how humans become pilots, right? There's a very straightforward path to getting a pilot's license that does a pretty good job, right? Most pilots tend to not crash aircraft. Clearly, this process works. But then the problem is that when we go to replace that with software, we realize that just taking what the humans do and automating it, it sounds like a much simpler question than it really is. And in this case, it's maybe a little bit easier to demonstrate when I talk about replacing a human pilot with an autonomous pilot. But for example, all of the manuals that we give pilots, human pilots, to read in preparation for the exam are written in a declarative way. So they're not like a set of instructions that one could translate into code, right? They just declare information about the weather is available over here. Information about this is available over here. And obviously the humans know in order to operate the aircraft around this weather system, I need to figure out what the weather is. So that means I should use the obvious method of extracting information from this weather source, right? And none of that is written. And it gets incredibly difficult to try to translate the declarative nature about how we write these sort of things into instructions that a human could follow. And then there's a whole lot of common sense that is also implicit in this that we never write anywhere. Like in both cases of autonomous cars and autonomous planes, we're assuming that the humans have self-preservation, right? We're assuming that the humans don't want to die, want their car or aircraft to emerge unscathed. We're making a lot of assumptions about what would make them comfortable. We assume that, for example, a human would hear something or see something and maybe they've never heard it or seen it before and go, oh, that's bad. My car is making a funny noise, or my aircraft shouldn't be wobbling this way. This vibration, this definitely feels wrong, right? Maybe I have never been tested on this, but humans have certain experiences that are built in, right? Humans would figure out, for example, and this has really happened, when the wing comes off of an aircraft, to look out the window and notice the wing came off of the aircraft and go, oh, that's bad, and here's exactly why. Whereas we would have to program some kind of vision system to be able to recognize that sort of thing. And that's not like, we don't have a whole large cadre of training data for that. So the questions are very, very different. And the way that we test and assess humans also can't be translated to software. So like, for example, we take a driving test where we demonstrate a couple of things in very safe scenarios. Similarly with flying, right? We fly the aircraft in a very safe way. And because we have demonstrated all the behaviors, then the instructor that is in the car or the plane with us is confident that if something goes wrong, we will know how to apply those same principles. But that doesn't necessarily carry over to software. And so, yeah, and in both cases, right, we take these multiple choice exams, and especially in the case of pilots, but some a bit also in the case of driver's licenses, there are multiple choice exams, and the assumption is that a human would only be able to figure out the answer if the human had internalized the information, right? But of course, an automated system can just take an exam with 500 questions on it, memorize a list of ABCDs, and spit them out, and it tells you exactly nothing about what the system knows about how this works. So yeah, those are the challenges there. Does that answer that question?
I think so. So we have another one, this time kind of going back to specifications. I can't imagine that verifying the correctness of specifications would ever be possible without human inspection and testing. Do you think we should aim at reducing the gap between English description and specifications? For example, designing domain-specific languages.
That's a really great question. I don't know the best way to solve this problem. Certainly domain-specific languages hold a lot of promise, right? They make the validation question easier. I also don't know that we'll ever get away from human inspecting specifications. I don't think we'll ever have humans not in the loop. But on the other hand, we need to help the humans. We need to find some way to help the humans come up with all the specifications, because ideally there should be a lot, and we don't want to miss anything. And then we also need to help the humans be able to validate it. So maybe a domain-specific language could be a great way to do that. Certainly several people have tried it. No one has completely solved this problem, right? There are definitely some automated checks that we have about specification. So for example, I wrote a paper some time ago advocating that as a specification debugging process, that every, for example, temporal logic specification and its negation and the conjunction of all of the specifications over the whole system should be checked for satisfiability by a satisfiability checker. That ensures that we're not over-constrained, we're not under-constrained, every specification can be satisfied but isn't valid, which also means it's probably not what we want, and then all the specifications can be true of the same system at the same time before we go and use them. But we don't have satisfiability checkers for every way that we can possibly write specifications. We certainly don't have them for English. And there are many different formalisms that we might use for capturing specifications, and we don't yet have satisfiability checkers for all of them. There are also other things like ubiquity or realizability checkers that are somewhat more limited, but also provide insight. So ideally, we would have some combination where we would have maybe some kind of wizard. Maybe the wizard would be based in a domain-specific language, and maybe the wizard would be hooked up to, all right, we have some databases. What are you building? Well, I'm building a UAS. All right, great. Let's think of the domain of UAS, right? Is it on Earth? Great. Then we have certain properties of how Earth works that we can fit in here, right? We know things about the physics of Earth and the environment of Earth and the rules of flying on Earth that are maybe different from flying on Mars or whatever, right? And so maybe we can then start answering the human and come up with some optimized way of trying to ask the human the fewest number of questions to assess what should the specifications be. And then in the end, I do think we're still going to end up with something like where such a wizard suggests specifications to a human, hopefully in a way that's easy for the human to understand, and then the human says yes or no or tweaks them or whatever. Maybe that looks like a domain-specific language. Maybe that looks like some kind of visualization. Certainly there are popular visualizations like state transition diagrams, or people have ways of drawing things, decision diagrams, or drawing timelines, or other ways of representing the evolution or different properties of a system. Maybe it's a hybrid of several of these, and then we collect them together. I'm not sure what that looks like.
Well, thank you very much. I believe we got through all the questions that everyone posed. So I just wanted to thank you again for the wonderful talk and the very, very robust question and answer session. And I guess we actually have the ability to continue using the Zoom room. So if anyone has any additional questions for Kristen, please feel free to ask them.
These have been excellent questions too. I'm glad there was so much participation.
All right, so I'd like to thank our speaker one more time. Thank you very much, and for spending a good chunk of time on the Q&A with us. I think we all learned a great deal.
Thank you so much for the invitation. It was a pleasure.
Thank you.